the
There you
gold
go.
back.
Thank you.
Thank you. Okay, so we're going to do some things on categorical data today, and we're going to talk about a question on the homework. So a couple people have asked the question, how do you do this one homework question? The 10.101 in there, right? So it's a case control study. So they have in the original table case and control, and they're looking at smoking. So 0, 1 through 20, or 20 plus, or more than 20 cigarettes. And they have these numbers 19, 19, 31, which adds up to 69. And then 69, 27, 27, which adds up to 113. 1, 23, 23, and all. And so the problem that I wrote that instead of using all the three smoking categories, let's collapse it to 0 versus 1 or more. So we're going to, this says to collapse this thing into 0 or more than 1 plus, 1 or more. Right? And there's cases and controls that are defined by another status. And so collapsing, you still have 19 and 69 over here. And then you have 50, that's up to 69. And then you have 54, and that's up to 123. And so that would mean by collapsing, just putting those categories together. Right? And so when it's like this, right, then there's two samples, two independent samples, and an outcomes you have to remember. Here's a handout.
Thank you.
And so one of them says make a confidence interval where the difference is in proportion of no smokers or the proportion of those. And so it asks, it just says, are rating of smoking different, or rates, I guess I should say, are rates of smoking different in the two groups instead of rating smoking? Are the rates of smoking different in the two groups? Compute a hypothesis test. And if you do the same question, are the rates of smoking different? Make a confidence interval. So P hat among the cases are rates of smoking. You could do it really either way. If this is the rate of smoking, you could take 50 over 69, and the P hat for the controls as the 54 over 123. And get your two sample things. And so it's two independent samples, two proportions. And based on these, then do a confidence interval or a hypothesis test. The hypothesis test would be a confidence interval for P1 minus P2. And this is in the hypothesis test, they're equal. And part C says instead of doing those two things, do a chi-square test. Right? Are these proportions the same in the two rows? It gives you the same result in terms of significance. There's a relationship between the z value you get for the test and the x squared value. The x squared is actually the square of the z value. It works out that way in that. But this is kind of reviewing the two sample proportions things and then doing a chi-square on that. So any follow-up questions? Does that help? When it's the original three-way, the 3x2 table, we don't have a way to do a confidence interval for, there's three proportions or three groups, right? So that one has to be the chi-square. If you have the original, collapse it, there's the equivalent between those things. Any other questions on that? Yeah?
It's not on the homework, but it was from the exam. Do you think that you could go over number 5?
So which one was number 5?
It was the normal distribution.
So if something is normal.
You want the actual test answer, dude?
Yeah, so sure. Great, I can look at it. So, right, so it's a normal with mean, some mean and standard deviation. And so there was some possibility for rewriting some of this question. So I'll give some hints, but I won't give the final answers, right? And so it has a probability that this fish is more than 60 millimeters long. And so X is the length of the fish. And if they're normally distributed, the length of the fish is normally distributed. It's going to be centered here at the mean. And so 60 is above that mean, it's 54 millimeters mean. You're trying to calculate this probability up here. And in our normal tables, one thing we know, right, is that the whole area is 1, and half of it is below and half of it is above. Oops. And so for all these normal problems, you z-score things before looking at the table. So 60 minus the mean over the standard deviation, and you get a z value. And so you look up this value in here in the table. In our version of the table, right, that we have for the z is essentially giving this area in here. So this is our little z value. That's our little z value. And we look up there, and it's not going to give you the probability is bigger. It's going to give you the probability between 0 and that value. So if you know that half of it is bigger, and this part is up to here, right, then what's the leftover? You wouldn't subtract this little part from 1, 0.5, right? 5 minus that area, that shaded area in there, so that should give that tail value. Now the part B is about 4 fish. So now you randomly picked 4 fish. What's the chance that? Now we're looking at the average here. This is asking what's the chance that the X bar, the average size, is bigger than 60 millimeters. Well, X bar has the normal distribution still. It's centered at the same thing as before, but its variance, what standard deviation is sigma over the square root of n. Standard deviation of X bar. So when you z-score, 60 minus the mean, you're going to have a different value down here for the standard error, and then go through the same process of calculating a tail area. Part of averaging creates the different variance in there. Does that help?
Yeah, thank you.
Yep.
So back to that homework question, would you just look at the probability of smoking, would you have to do probability of smoking versus non-smoking versus casing? Because that would give you 4 different.
Right, it could give you 4 different things, and it'll work out. You can just pick, smoking versus smoking rates, comparing the case and controls.
Okay.
You can really do either one.
Okay, so you don't have to do both.
Right.
Okay.
Numerically, the difference between smoking in the 2 groups is going to be the same as the difference of non-smoking in the 2 groups. It just will be minus. And then the standard errors end up being the same, because in the standard errors it's p hat 1 minus p hat. So you take smoking or non-smoking, you're just taking the probability of smoking times the probability of non-smoking. That enters into the standard error. So the numerical values, the result, all however you view it, end up being the same. But any other questions? Right. So do submit so the homework, just the manila folders, there'll be a yellow folder, this yellow folder will be sitting out there and say 140 on it, and you just put this in there. Right? So this is a great technology for saving in terms of office paper. This envelopes like this get used couple hundred times. But anyway, that'll be there. The TA, the teacher, the grader will come and get those later on Friday. If you missed that time or it's not there, she's come and got it, and you've completed it, go ahead and put it under my door. Then we'll get it, by Monday and start to include it then. So the main, okay, the second. Any other questions? So if you're rewriting that portion of the exam on that normal problem, be sure to hand that in pretty soon. In terms of just a little bit outline, upcoming schedule. So I've gone this Friday, and then Monday and Wednesday we come back. We'll be looking at things in chapter 11 on linear regression and prediction. There. And then there's an Easter break. And then we don't come back until Wednesday. So after that break, we would do a little bit on chapter 12, kind of introduce analysis of variance. Both of these two things we won't be doing, complete treatment of all the complexities, but there are very common methods in biology, medicine, other fields. I think within the scope of the things that we can understand, it's good. We will be a very applied approach. Here is generally the research question we want to apply, a little bit of the structure of the data, and how some of the output looks. And then, really Monday, Wednesday is the last weeks. We'll really have a review and summary of things. Given that the homework due on Friday, and then we'd have a couple new days on regression. The next homework, since homework 10, would be due after Easter. Yes?
Where does the project fall into that?
Yeah, so the project falls at the end, right? The project comes at the end. It would be homework 11 to do a short illustration on analysis of variance in there. But things kind of get spread out because we have all these partial weeks, but the project is due at the end. So on Friday, when we don't have the class meeting, you'll finish up the homework. Encourage you to start looking at the project. You get something identified that you want to do, this next week. Make sure you have some data. It gives you a couple weeks to put something together. There's the Easter break, which of course you might be doing other things, but and so you have enough time, so you're not doing it in this last week. There's a big crunch at the end because finals and all the classes happen so close after that. And if you can get a data set for the project and kind of get some hypotheses and things you want to work with and make sure you get started on it, then it will probably be more enjoyable experience than trying to rush it quite as much. So that's that. And today we're going to look at some categorical examples of things. First, in terms of kind of general perspective, I guess, on things. As we started really with the course, that a lot of things really start with a research question, something you want to know. Someplace where there's a gap in knowledge or gap in understanding, and you want to really try to understand how the world works or how things influence one another. So you have a substantive research question that you can't find the answer to. You do something to collect data related to that. Could be a survey, randomized controlled experiment, more observational data, some quantitative variables, some discrete categorical variables, and things. Phrase those in terms of statistical hypotheses you want to look at. part of describing the data. You have data on different groups, you look at those, you have the smokers and non-smokers, you can get rates in different categories, numerical, graphical. And then statistical inference. Inference for the unknown parameters. Things get graded in terms of means, proportions, variances. Once we do linear regression, there's going to be a slope or rate of change that we're trying to estimate. Maybe we do confidence intervals, maybe we do hypothesis tests. And then after that, there's some conclusion. And one thing we're seeing as we go through these different methods is if you have different data, if you have one group or two groups or multiple groups, if you have quantitative data or categorical data, and so on, this inference, the inference method, inference procedures, that are used, the ones that are appropriate to use, you can see that they depend on structure of the data, structure and type, and also really kind of the size of the data. One sample, two samples, is it paired or not? You know, if we have large samples, normal approximations and things like that work out better. Some of the things that are described as exact or alternative procedures sometimes are for small sample sizes. So keeping track of which to use where is an issue. In the book, right, are some of these charts, right? So in each of the book really has a kind of decision framework. Right? And this one, this would be one of the flow charts that's in there in the book. And so in this one really is a flow chart, right, about statistical inference procedures. And then we have two or more samples and its categorical data. So this is one little snapshot of the decision that you might think about in deciding what to do. So most of our samples are described as independent samples. That's what we've done so far. So you have cases and control. You have one sample of them and another sample. More of a designed experiment, you have the treatment and control. Where you take a sample of this group from this area and a sample of this one. So they're independent samples. If they're the expected values, we have these 2x2 tables, right? So you want a certain sample size. If the expected values are all greater than 5, you could use things for contingency tables, using the chi-square distribution or normal samples, normal distributions. If it's just 2x2, right, then we're in this case where you could have two binomial proportions, like the example from the homework at collapse 2x2. You could look at two proportions, do confidence intervals, hypothesis test, or you could do things for a chi-square test for 2x2 tables. That works out. There's something in here called Mantel-Hansel, right? That is the idea of we're not going to study this. Sometimes it's called. Sometimes there's some confounding, in the sense that our sample has distinct subgroups in them. So maybe you would, split, the subjects by age. Maybe you have some older subjects and some younger subjects, with 2x2 tables, if these are split into not just one 2x2 table, but you have a 2x2 table for the youngest group, and a 2x2 table for the middle group, and a 2x2 for the oldest. It's called multiple tables. It's called stratified. Multiple 2x2 tables. Sometimes it's called stratified 2x2 tables. And there's methods. It's Mantle, Hansel, I'm not sure exactly how to spell that last name, right? Procedures, and so sometimes it's called Cochran, Mantle, Hansel, because there's different people that kind of develop things separately in there. Right? So anyway, if it was that case, and there's this confounding, it would suggest a different inference procedure. You would look up those things, and in that article, that New England Journal of Medicine article about the hypothermia cooling in infants that had difficulties in birth, that was combining different studies. And then so the different studies, every study gave you a 2x2 table. So you had 5 or 8 or 16 2x2 tables. And they used these methods for combining results. We're not going to do that as a particular thing, but if you're ever in that situation, you would have a possibility. So A says you could do that. We would just do the things in there. If it's 2 by K or larger, right? If it's a 2 by K proportions, you can do a chi-square test, or there's actually, you can test more if there's a trend. I guess I'll go back to this thing. So we have 2 categories, smoking, non-smoking, but against a bunch of age groups. You know, you could go down here and you can do those things. We've been more concentrated on our chi-squares here. We have tables. We're interested in are the variables related to one another, and so we've done some things like that. So we've done some of these methods. Where exactly you would end up and what exactly you would do depends on the structure of the data and things like that. Underlying all these is a lot of the same principles. Right? And there's some hypothesis that tells you about what the data should look like for that type of data if there's no association. And then you think about what the structure would look like if there is an association, and come up with some test, right? Some statistic that is typically has a small value if it's consistent with no association, a big value if it's consistent with heterogeneity, and if it's big enough, according to some distribution, then you reject the null hypothesis. If samples are not independent, we'll talk about that briefly. There's this other test. That's not particularly hard to implement, but a lot of times things look like they're 2x2 tables, but really there's this kind of matched pairs going on, thing going on. So let's look today at an example of a 2x2 table. We're looking at it different ways. Right? So here's an example from Samuel's book et al. It's their problem 10.3.8. That's there. The data, there are 21 acres in a study. They identify on these 144 different quadrants. They're different plots out in the wilderness spread around. And on each of these 144, they go out and look at them and decide whether there are hickory trees there or maple trees. And they could have both, right? So each plot gets measured on both things. Presence or absence. Present and absent. And maple could be present or absent. And so there's 26 where they're both present, 63 when it would be just hickory. So there's 89 here, 30, 25, 55 there, and this adds up to 56. This one adds up to 88, and all add up to 144. And so a question comes out of these data: are the presence of hickory and maple trees independent of one another? Right? Do they tend to grow together? Does one discourage the other one? Is there any interaction between these species? are the presence of maple and hickory independent of each other. So, that would be describe the data. What descriptions would be? So the table's descriptive, but you can calculate proportions too, right? Overall, the estimated probability that there is a hickory tree, one of these plots. Out of hickory, there's 89 out of the 144 that are present, or about 62%. The chance that the maples are present by themselves. I'm looking on this margin, that was the maple one. 56 of them had maple trees, so 0.389. Those are not 1 minus each other. It's not like a trade-off. They're close to 1 minus, but they're not 1 minus. They're just the rate of hickory or the rate of that. But that doesn't really say if they're dependent. You might want to report that anyway. What about, what's the chance that you have a hickory tree when there are maple present? Put these little hats over there because it's taking it from the data. So when there is maple, that's this column, right? That's this column over here. Right? So it would be 26 out of 56, which is 0.46. What's the rate of hickory trees when there's no maples? When there's no maple, as the maples are absent, right? It's this one over here. So this one's going to be based on this column. Well, there's 65 out of 88. A lot more, 72%. Is that? So what does this give the impression? What impression do you get out of this?
Plus
Good enough. Yeah.
That maples and hickories are dependent of each other?
Yeah. So there's some dependence, right? This does not look like independent, right? It's a hickories, overall it's about 62%, but it's less when maples are there. It's more when maples are not there. So maybe they're fighting for space. It's a really simplistic biological hypothesis, but resources and space. So yeah, so there's these two proportions, right? So based on that, what could we do, right, if you wanted to do inference? You could do a 2-sample proportion test. Right? You could do a confidence interval. These numbers could lead to a confidence interval or a hypothesis test using two samples, two tests for 2 proportions, 2 independent samples. In there, and you can try to come up with some conclusion. But it looks like they're not independent. Another way of doing this would be to do a chi-square test, and that's what we've been doing in this chapter. We could do a chi-square test. So the original data we had was this 26, 63, 30, 25, and I'll write the margins up again and the totals. 56, 88. So if independent, if these things are independent, then we can calculate expected values. how many plots would we expect to have? This was hickory and this was maple. This was present, absent, present, absent. How many plots would we expect to have both hickory and maple? How many would we expect to have one but not the other? And how many would have either? Well, the expected values turn out to be, let's calculate them. The expected values end up being 34.6, 21.4, and ends up scoring 50, 89, what? Okay, 21. Oh, it's 21.4 down here, I guess. 33.6, and this one, reversed on my 54.4. 4. So that adds up to 88, that adds up to 89. 50, 54, 55, 144. And these things add up to my 56 and 88, right? Where did something like this come from? Well, we have the 88 in that column. But if the rate of being in the top portion is the same as overall, it was 89 out of 144. So you just multiply really the two outside margins divided by the sample size, and it gives you that expected number. How do those compare? Where do we have less? Yeah.
Where degrees absent is equal to present.
So we have kind of, this is where they're the same, both present, both absent, right? So we expect 34, 33, about 34 on each of those, right? But we only have 26 and 25. So the occurrence of both, or the absence of both, happens a lot less than we would really expect. On the other hand, off the diagonal, right, we expect only 21, we expect 54, but we have more. So they seem to trade off like that. That would be a description of this trade-off. And so we're going to calculate x squared statistic. Calculate that from this output, we actually get 9.18. We have a degree of freedom, 2 minus 1, 2 minus 1, and just 1 in this case. And the upper 90.95 tail of this distribution is 3.84. If we look that up on the table of chi-square values. So if they're really independent, we wouldn't expect to get much more than 3.8 for that kind of square. But we got 9. So what's out there? We would reject independence, include that there is some dependence there. It is pretty strong information. So on the handout, on the back side are some commands. Right? For part of the work on the assignment, you can do some of the things in R. This is how you would set up a little matrix, a 2x2 object that would hold just the counts. Right? These are our numbers. So just like this, so that part of it would just give you 4 numbers. Right? But I'm going to put it inside of a matrix and say there's going to be 2 rows and line these things up by row. Oops. And then, so the matrix does that. I'm going to save it as this thing called DAT. So DAT is now that 2x2 object. I don't have to retype that same thing all the time. The chi-square test gives these expected values. In there. This is the continuity correction for testing. It doesn't really affect the expected values, but it would affect the test statistic. And if you do the chi-square test, it gives this output. It spreads it out a little bit. I compacted it for the handout. keep it on one page. But it gives us statistics, degrees of freedom, and the p-value is this 0.002. And so p-values that are less than 0.05 mean reject. There seems to be a significant association, and these trees really, you might think biology, yeah, they probably trade off from each other. Some things, though, are synergistic and kind of go together, like, in things, and so good. But in this case, it does not appear to be that way. They're probably fighting for space. A probability chi-square gives a tail area. A probability you're less than that chi-square. And so 1 minus that gives the 0.002 p-value. Cutoffs, chi-square with 1 degree of freedom, the 95% upper point is 3.84. Right? The 99th percentile one, which would correspond to an upper tail of 0.01, is that. But we're beyond that one even. We're not beyond the 0.001 tail. So these are quantiles or percentiles there. Right? If we wanted to implement in R the 2 sample test of equal proportions. Now these are all ways of getting at the same information. It's going to be the same conclusions, a lot of the same results, but depending if you look at it different ways. So these would be the data if you're looking at the presence of hickory with or without maple. There are 56 times with maple and 88 without. And with maple there was 26 hickories, and without maple there were 63 hickories. And so that's the command that implements the 2 sample proportion test. So if you check that out, see the x-squared value is the same, p-value is the same. These are the estimated 2 proportions. And I give the 95% confidence interval. It's less than 0 because of the way I set it up by taking the one that did it. Less maple to begin with, right? Or you could look at it the other way, right? You could look at maple with or without hickory and look at the other direction. You get different confidence intervals and things, but in terms of testing, you get the exactly same chi-squared value. It depends on how you're stating the question. Now these are not so small sample sizes, so I think this would be perfectly fine. You could put in that continuity correction, and some people would say that that would improve the accuracy of the p-value a little bit. It's not going to change overly much in this case. There is this other thing called the Fisher's exact test, which calculates probabilities under a binomial and not normal. That's another way of getting at a p-value. And it's for when there's small sample size. We don't really have small sample size here, so it wouldn't necessarily be required. But if we'd only had 10 plots or 20 plots or 40 plots even, we might have ended up with some pretty small expected values in some of those. So the DAT was my matrix. If you put that into this Fisher test, it gives you a p-value pretty close to what we had before. A little bit different, a little higher, not too much different. It does get a different, it focuses on the odds ratio. So this is actually a confidence interval for the odds ratio. Why is this is still significant? Because it's below 1. Right, so it's a different statistic. It's still trying to do inference for this. And so there are multiple methods people have made up for analyzing the same things. Mostly, you would just need to do one of these things. So a project could take 2x2 data, look at it in proportions, look at it in a hypothesis test, look at it in 2x2. That would be comparing methods, and you could demonstrate that you get the same procedures. And so this project could kind of go through these different steps: research design, describing the data in different ways, and so on. Yeah.
Can it be in like first person, or it doesn't have to be?
Can it be in first person? I mean, I guess I would try to make it consistent throughout. I mean, a lot of scientific writing and things goes into third person, or it was observed that instead of I observed. And so, but I'm flexible.
Okay.
I think it's best practice to keep it consistent.
Okay.
In terms of tense, maybe past tense, like I did this, or some people write things all kind of in a, if we look at this, then we see this, and, you know, so trying to keep tense the same, perspective the same. And so you can use first person, you know, even with using first person, minimizing the number of sentences that start with I, right, makes it a little bit nicer to read, a little varied in language, but yeah. But it's not a strict scientific paper
Okay.
that way. So let's look at a second, right, example, right? So in, this is also from Samuel's book. I think they're relevant examples. By showing examples from another book, you wouldn't necessarily see those by just looking through our book. So it's very similar to in this problem for them. There's 2,287 patients with coronary heart disease. And they're randomized. It's a randomized controlled trial. They're probably not the most severe, where you have to do some emergency, and maybe not the ones that are clearly mild, where you wouldn't do angioplasty, but they're kind of candidates for either one, kind of at the borderline, hopefully. And so some receive angioplasty plus medical treatment. And the other ones just receive standard medical treatment. So the question we have is it worthwhile to do this extra procedure? Any surgical procedure, any more invasive procedure has some risk, so it doesn't really work out for that. So their data has, there's the angioplasty group, and there's the ones that are just doing medical treatment. Their outcomes are cardiac death, other death, unknown death, unknown cause, so people could have gone home, they could be at another state or something, and they just know that they died because they, you know, there's something called a death registry. There's a national death index that has compilation of death certificates. It's a federal thing, and so they might know that people died, but they might not have access to their medical records to know why they died or exactly that. And then others, people who were still alive at the end of the study. So 1149, 1138 is total in here, 23, 25, 48 cardiac death, 45, 96 other death, 17, 19, 6, and that leave most of the patients still alive. 210. There's the table, and it counts. Is there a difference between these in terms of these different categories? Numbers are pretty similar, right? The denominators, 1149, 1138, are pretty similar. So how can you describe the data? How could you communicate this? Right? So with tables, you can kind of judge, but you know, some people are better at judging what it would end up being if you divide. You could just simply divide. You could just convert this all to rates. So these four categories. Angioplasty one, this is the medical treatment. To abbreviate. Out of this, right, so we're going to divide so that these adds up to 1 in each row. Okay? So we're going to look at the chance of each of these outcomes in each group. This is about 2%, but over here it's 0.22. This is 0.319, 0.0, no, sorry, 39. .015, .017. I had to kind of go to 3 decimal places to get much of a description of the difference. 0.926 and 0.917. And if those don't add up to 1 exactly, it's because they're rounded. And once you put in these percentages, that doesn't look too different, right? To me, it doesn't look too big of a difference. A little bit of a difference there, but still pretty small. Now we're going to calculate the chi-square statistic. So one question I might ask is how many do you expect, say, to have in a particular cell? If these are independent, if these are the same rates of disease, of outcome by group, how many would you expect to be there? Tests I usually don't have you fill out the entire table, but I might ask you about one of these. So this one, you expect, well, we had 36 in this column here. There's 2, 1, 4, 2, 2, 8, 7. I don't know where overall. So the percentage that's in this row, kind of at the end, 1138 over 2287, would be the fraction. It's about half. We expect about 18. I don't have the exact value, but it's about half. Right, about 18 there. So it's 19, expected value of 18. It's pretty close. Seems to fit pretty well as a model. If you do all that and add up the chi-square statistics, the x-squared statistic ends up being 0.73. The degrees of freedom we want to use, there's 4 outcomes, 2 groups. So there's 3 degrees of freedom. The chi-square with 3 degrees of freedom, the 95th percentile, is 7.81. So if this is our chi-square picture here, this is our chi-square redistribution. 7.81's out here. Up here is where we reject the idea that there's equal outcomes. And we are back over here, 0.73. Really small, close, very close to matching the expected values with the observed. So we don't reject. There does not seem to be a significant difference between these 2 medical procedures. And if angioplasty has any other, well, this says it doesn't really benefit, so maybe there's an extra cost is the main downside. Maybe it's more discomfort by having this, so patients might not like it. But it doesn't seem to be worth it. In R, on the handout, you can enter data like that without a whole lot of trouble. So here, going, is that not on the handout? Right. I did it though. So what are the data? So to put a matrix like that, so my second data set, let's get to the top up here. The second data set, we want a matrix, right? And we want the counts 23, 45, 17, 1064, and then the second row is 25, 51, 19, 1043. That little space in there really doesn't do anything. It just makes it easier for me to read it. We want 2 rows. There's 4 columns. You really only need to specify one of those things because it figures it out. But by row equals true matters. So there's that full command. And there's our data. And then the chi-square test, our DAT. And I'm not doing the correction here. And we get our statistic, degrees of freedom. It says the p-value is very large. Right? The chance we're above that point, we're way back in the middle of it, so it's more than 50%. Not unusual at all. Do not reject. The cutoff, the quantiles for the chi-square distribution, it's like the 0.95 cutoff with 3, it's a 7.81, so we'd have to be beyond 7 probably above 8, really, right? Something like that to get a significant result. So it does not appear to be beneficial. This data does not prove that it's a beneficial treatment. Medical therapy for the patients that are of this type seem to be pretty much equal outcomes. So if we had 4 outcomes, we would change our inference procedure. Well, we'd be kind of pushed into this one. Right? Now, the final thing I wanted to mention is this. You can have paired data with categorical outcomes. So how does this, we won't have to know this for an exam, but just to point out that, here's another different type of, the data structure is different. We use a slightly different method, and that's why there's all these different varieties of things. Yeah.
Can you just go back to that last slide?
Yep.
And can you just explain how to read that graph? Because I'm kind of confused.
This graph,
Yeah.
right? So this is, so if there is no association, right, between, in this case, between the outcomes categories and treatment, then our x-squared statistic in random samples of this size follows this chi-square 3 distribution. So our value of x squared is what we're going to put along here. And if x squared is way far from 0, then we don't believe that there's no association. If x squared is near 0, right, so what was the formula for x squared? X squared was a sum over all of our cells of the table of the observed minus the expected squared over expected. So for each cell, if the observed and expected are really close, like they are in this case, then that's small, right? And we don't get a very big accumulation of chi-square values. In the first example, observed and expected were really quite different, and so we get a big value. And so if it's beyond, this is the 0.05 scale area, out here, 5%. So if it's up above the 5% cutoff, if it's that extreme, right, then we reject the idea that it's independent. But that model of independence that gave us expected values does not seem to be accurate. On the other hand, like this case, it's pretty close. Our chi-square value is nice and small. Sure, that's perfectly fine. Could happen just by chance. So how do you get paired data? Well, let's say you have sunscreen. We're going into some warm weather, hopefully. And you have sunscreen B. Right? And you have a bunch of volunteers. And they flip a coin, heads or tails. And heads, you put A on the left arm. Put the sunscreen B on the right arm. And if it's tails, they put A on the right arm. And you put B on the left arm. Some people might use the left arm or right arm more for different things or explode, And then what you're going to measure is do they have a burn or not? In either case, you're going to, for both arms, you're going to burn or not. They're going to be exposed to the sun for a certain period of time. Are they going to still burn or be protected by one more than the other? Right? It's matched pairs because each person contributes 2 measurements on this. Right? And so you would summarize the data on the A arm, burn, no burn. And I had to write no burn up here at top and burn down here because it's the way I did it in the little notes. And for the B sunscreen, no burn, burn. And you're going to count the number of times these different things happen. And these ones here with the matched pairs have no difference. They burned in either case or they didn't burn in either case. Right? So there's no difference here. You can't use the ordinary things that we do with two independent samples because you can't say whether it's A burn and B burn. And there's two differences because there aren't two different samples. They're correlated. Some people that are very likely to burn both times are likely down here, and some people that seem more resistant because of pigmentation or something or activity level or something are up here. So they're related. So they're not independent samples, and the variance is not the sum of the variances.
Yes, so you said that there's no difference between A and D, so they're not.
Yeah, so the result for an individual on the left and right arm is the same, no burn, or burn, burn.
Could the same be said for B and C?
B and C, it's discordant, right? B and C are called discordant pairs. I have on this one B, I have A on this arm and I don't burn. I have B on this one, but it's burned. Right? I get one person is getting two different results. Right? It's called discordant. So this gets tested with something called McNamara's test. That says if these are equally likely, if these are equally good, right, B and C should be equally split. There should be the same number of A doing better than B and B doing better than A. It should be split equally. Right? So basically it says B, the number that are in B has a binomial distribution. There's B plus C discordant pairs, and they should split out half and half if A and B have no difference. That's essentially what it's doing. You're not responsible for this, but it's kind of in keeping with the whole idea that, I mean, if you want to do something for a project and read this chapter and figure this out, you could do some data examples and explain it a little bit more. Let's say you had a 80 subjects, and here's A and B, and 24 times and 36 times were here, but there were 8 times here that this is burned, and this one was burned. So 8 times B avoids the burn, but A does not, and here 12. Is 8 and 12 an unusual balance if it's supposed to be 50-50? It turns out that the probability that this number over here, this is actually like we'll see, the chance that that is greater than 12 if the probability that these 20 would split equally between these different pairs is about 0.252. So about 25% of the time we get something as extreme or more extreme than that type of split. That's not too unusual, right? So the value for testing, are these equal or not, is about 0.504, so 2 times this. If, on the other hand, we had the same number of discordant pairs, right, but they split as 4 and 60. Right? And so this one, B, is burning, right, but A is not. So A is kind of looking better. We don't do a 2-sample independent test because of this matching there, that explicit data structure. This case, the probability that that C would be greater than or equal to 16 given P is 1/2 is 0.2 .006. So our p-value, 3.012. So it does appear, if we had got this matched pairs experiment with people each getting one of these things, right? And we got discordant pairs that were imbalanced like that, then the two things are not equal. So it's a different data structure, a different test, but very much grounded in the probability and things that we've done. If you get large samples, there's a normal approximation of that one too. So again, the design influences the test you do to try and answer your important question about which sublog to wear. All right, we'll see you on Monday. Good one. Yep. Oh, thank you.
But also, you said we're going to be getting
Bless you.
Something like that. I'll take a look. You know, so probably at least 10.
Okay, yeah, thanks.
Yep. Thank you. Oh, great. Thank you.
Since we just went over the client problem, would and when is it that due? Friday?
You could put, like you're putting on a sheet, or you're gonna write it on the exam. You could, why don't you slide that under my door instead of putting it into the grading.
Okay. So do you want me to have the
You
exam
could
back?
write out you could write it on a separate piece of paper, or you could just slide the whole thing underneath. Either one will work.
Okay.
Okay.
I just have more of a question on 5.
Mhm.
I just like I thought I did it, and then when we looked at it in class, I just got more confused. And
So you're getting the right z value. What's the
Yeah.
probability that z is greater than 1.33?
yeah, like I get that part,
Mhm.
but then when it comes down to here, well, first of all, for this, you said it has to be like 0.5 minus. Then I have a negative, and then that doesn't make sense in my mind.
So if you just use the 0.4082 here, so
Okay.
what number do you look up? So 1.33 gives you
Yep.
what, 0.4082? Is that what it is?
I don't think Menzies put that table on there.
Oh, all right, maybe I said the other, right, so if you look up so 0.9082, if you just take 1 minus that, I goofed. That in my other class, it's just that portion of a table.
Oh, okay.
So it cuts off the 0.5. So you can just 1 minus that. So
Okay.
That's fine. Okay. 3 books, 3 normal.
Yeah, no problem. So then that gives me that number.
Yep.
And then I can, so then when we get to B,
Yeah.
I have this, but
Yeah, yeah, so it's a bigger number.
so then
So you look up that z value.
for 2.67.
Go in here.
9962, which is this one.
Yep. So that's the probability, yeah, that's it.
Oh, okay. Let me do
It's
that
a lot,
one.
the average, to get above the 60, which is a pretty big value,
Mhm.
for the average is really unusual.
Yeah.
Because the average pulls everything back toward the middle, pulls it back
Yeah.
to 54, so.
Okay, let me do that math and then I'll give it to you.